Hello everyone and welcome to today's webinar. On behalf of American Petroleum Professionals of Iranian Heritage, APPIH, it's our great honor to start another webinar entitled Method and Tools for Geomechanical Modeling of Reservoir by Dr. Zamiran. Dr. Zamiran is a geotechnical and geomechanics engineer with over 15 years of industry and academic experience in different geotechnical and petroleum engineering disciplines. Currently, he is a geotechnical and geomechanics consultant and an adjunct professor at Missouri University of Science and Technology. Dr. Zamiran is a member of ASC Geo Institute Computational Geotechnics Committee. He was a winner of the National ASC Edmonds Friedman Award in 2019 and ASC St. Louis Young Engineer Award in 2018. I would thank Dr. Zamiran for accepting our invitation, and without further delay, I'm transferring the microphone to him for starting his presentation. Thank you.
Hi, everyone. I hope you are doing well. Thank you, Dr. Samui, and also thanks to APPIH for inviting me, for providing this presentation. I'm so excited to be here and being involved as a speaker in this presentation series. So without further ado, I'm going to start the topic, and I will start with a brief introduction to numerical modeling, and then I will provide descriptions of methods and tools, topics with regard to constitutive models, geometry development of reservoirs, and then I will provide a couple of different practical examples to show the usage of geomechanical modeling in wellbore stability, flow mechanical, wellbore analysis, thermal modeling, and fracture modeling. So very excited to provide this presentation. As Dr. Samui mentioned, my background is in geotechnical and geomechanics engineering, and I provide consulting and educational resources for geomechanical modeling of underground reservoirs. And that is obviously an interdisciplinary major. We provide consulting to oil and gas industry for sure, and other industries that we are focused on. That includes also mining and undermining industries. That includes open mines as well as deep underground mines. And then other industries such as underground excavation for tunnels, and then getting to the ground surface, more geotechnical aspects as well. So I want to start the presentation by providing an introduction to numerical modeling and the usage of the numerical modeling. So numerical modeling is basically computer simulation. So using computer programs to simulate a physical system, and then by simulation of that physical system in computer, we can study the behavior of systems and proceed with some types of analytical solutions. Once we are talking about numerical modeling, specifically in geomechanics, sometimes we also call it numerical modeling in geomechanics. Also, we call it computational geomechanics. So all of them follows the same procedure and methodology. So once we discuss about numerical modeling, we mostly deal with three aspects during any investigation. The first aspect is the physical system. The physical system is the actual realistic system that we are interested in modeling it, for instance, an underground reservoir or a well bore. That is our actual physical system. Then we have mathematical system. The mathematical system are systems that uses mathematical equations, closed form solutions to predict the behavior of any physical system and any physical component. And then we have the numerical system that, as we mentioned, using computer simulation for studying and analyzing a physical system. And the application of numerical modeling, we can categorize that into three different areas. In general, we use numerical modeling for interpretation of a system. So study the system and provide interpretation of the behavior of that system. We can use it for design, obviously. So let's say design of the wellbore. In the first case, we already have that system in the real world. In the second case, we don't have it. We are just using that to design an efficient system that would be safe for the case that we are studying. And then the third is the prediction. So we can use numerical modeling and develop a model for an environment, for a medium, and apply some alterations to that model, and then predict what we'll expect after those alterations have been applied to the model. So basically, it's a very powerful tool for us that we can use that to simulate complex geometries, complex models, and then interpret, design, and predict those models. And one of the things that we need to understand and make sure that we consider that is the idealization of field conditions in numerical modeling. So in many cases, obviously, any field model, any realistic model has a variety of complexities. The reason is because we live in a world of complexity. We live with complex systems. And therefore, we need to deal with these complexities, obviously. So for dealing with these complexities, we need to use some level of idealization once we want to do a numerical model, because we are not able to develop a system that fully model the whole complexity of the system. So to some extent, we do some idealization. For instance, this is a cross-section of tunnel. There might be some level of complexities with regard to the layers of the rock, or vegetation, or different materials around the tunnel. But in the numerical simulation, there will be a more simplified condition. Obviously, a more sophisticated model, a more accurate model includes more complexities of the real world. So the goal of this seminar is to provide a brief and a glance overview of using these numerical modelings for geomechanics simulation. Obviously, we are not going to get into details of all these different types of procedures, and obviously the topics that we are providing in this seminar is very, very broad and extensive, and obviously we cannot provide the whole subjects into just one seminar, but we just try to get a feeling of these different methodologies and approaches for geomechanics simulation. So in any cases that we want to run a numerical modeling for the geomechanical simulation, we have different steps for that. These steps starts from the idealization of the field condition, as I mentioned, and then choosing of the numerical method and the program that the computer simulation tool that we want to use for that. Then we need to develop the geometry of the system. And after developing the geometry, we'll develop a constitutive model. That's a model that represents the physical behavior of our system. And then assigning material properties to our computer simulation. Then any loading or boundary conditions should be applied. Initial conditions are applied. And then if we have any alteration, for instance, some type of extraction or drilling, that can be applied in the also computer simulation. And then we get to the analysis phase. So we analyze the model, and by analyzing the model, we'll get the results. And then we can interpret the results and use that for those applications we mentioned: interpretation, design, or prediction. So this is the general flow of any numerical modeling, from observing the real model to measuring to modeling, analyzing, and getting results, and then explain them. The way that I organize these slides and this seminar is based on the procedure that I discussed here as well. So the first thing, I'm gonna provide a brief review of different methods and programs that are available. Then I will talk about the geometry development and tools and methodologies for that. Then I will talk about constitutive models and some typical types of models for geomechanics simulation. And then I will provide some real case examples of that these modelings have been done, and providing some results that we can expect from any numerical simulation. So the first thing that we talk is the methods and tools. Again, as I mentioned, this topic is very broad, and I provided here just the most important ones, but obviously there might be additional methods and tools that will not be addressed in this seminar. So don't expect just all different methods that's going to be provided here. Our focus is more into geomechanics simulation, and then as I will discuss, my main focus will be on some types of computer programs that are mostly used by geomechanics engineers and geotechnical engineers. So firstly, let's talk about the methods, and then I will discuss the programs that are developed based on these different methods. The first method is finite element method. This is the most common method that is used for computer simulation of not only for geomechanics, reservoirs, and medium, but also for other types of engineering and for other engineering disciplines, from structural engineering, mechanical analysis, to biomedical engineering, to soil mechanics, and all different aspects of engineering disciplines. The base of the finite element method is developing the stiffness matrix of a system, and then by force equal to stiffness times displacement, and by doing the matrix calculation, we can estimate and we can analyze and determine the amount of displacement of a system by applying the force to that. So that's the classic methodology for numerical modeling of any system, as I mentioned, from structural components to geomechanics medium. The procedure would be very similar to what I discussed for numerical simulation. So again, we'll have the geometry, material, boundary condition, loading, and solution. And once we develop the finite element modeling, our whole model will be divided into small elements. And then during the computer simulation, each of these elements will get a stiffness matrix, and calculations will be performed on each of these elements as a whole model. One of the other methods that are more used in geo environments is called the finite difference method. That is older and simpler technique, rather than the finite element model. It does not include matrix calculations, and it is based on equilibrium equation between stresses, strains, and displacements. One of the advantages of this finite difference method over the finite element method is that in finite difference method, because we don't have the matrix establishment, the amount of movements and deformations that can be tolerated in the model and considering the computational time would be higher. So although we'll have larger deformations in systems, the computational time would not affect considerably. That's in reverse, in contrast of finite element models, that in a large deformation models, the computational time increases as well. So we know that in geomechanics environment, in soil and rock environments, we might have extensive deformation. And for that reason, the finite difference method would be an idealized solution for geomechanics modeling. And then in finite difference model, we also have those elements, as I mentioned, in finite elements. So a finite difference model is also divided into smaller elements that each of those elements will be analyzed in computer and investigated in the model. However, the terminology that is used for finite difference, we mostly call them grid or zones. In finite element, we call them elements. But still, element and grids are components of a model in both FE and FT modeling. The third methodology that is extensively used in geomechanics modeling, and more specifically in the mediums that are jointed and fractured, is called the discrete element methodology. The discrete element methodology, it's also called the distinct element method. So this method consists of modeling blocks of materials that are separated by fractures and joints. And the procedure for the interaction of these elements along those joints or fractures are based on the stiffness, based on the springs and dampers that are that connect those different blocks or elements together. And by these springs and damper simulation, we can simulate the fractures and the joints between these elements. Another categorization for that methods is called the hybrid methods. So hybrid methods basically includes methods that combine the different methodologies that I mentioned, for instance, discrete element with finite difference element. So one important note here, comparing the discrete element and a finite element and finite difference element, is in discrete elements, we mostly have jointed and fractured components between the elements. However, in finite element and finite difference models, the whole model consists of continuous material. We don't have fractures or joints in the model. We have elements, but these elements are just for computational application, and then there is no fractures or joints at the boundaries of those elements. So that's an important distinction, and that we'll discuss about the applicability of these different systems. So by categorizing the software packages that are available for geomechanics modeling and considering the different categorization, we provide a list of these available tools that can be used. I categorize them based on continuum modeling and discontinuum modeling. As I mentioned, discontinuum modeling is modelings that consists of fractures and joints. And continuum modeling considers modeling of areas that we have continuous material without any fracture or joint. As I mentioned, finite element and finite difference both can be categorized under this continuum modeling. The available tools for continuum modeling for geo environments like geotechnical and geomechanics usage. In finite element, we have programs such as Plaxis, Sigma W, Midas GTS, and RS. They are programs developed by different companies and entities. And then in the finite difference model, we have FLAC and FLAC 3D as two powerful tools for that. For discontinuum modeling, there are tools that are available for modeling geomaterials. A couple of them are UDEC and 3DEC, and PFC2 and PFC3D. So the difference between UDEC and 3DEC and PFC2 and PFC3D, although both of them are based on discontinuum modeling, but in PFC2 and PFC3D, we basically have particle modeling. So the models are divided in particles, and then there are joints between the particles. So it's probably useful for granular soils, for example. UDEC and 3DEC are based on deformable blocks that are discretized into internal constant strain elements. So these are blocks that they have joints and fractures in between each other. So it's a different approach by same type of methodology. And then these models can be also combined and coupled together for having the hybrid modeling as well. There is another model, it's called limit equilibrium, that is mostly used for geotechnical perspective rather than geomechanics. Keep in mind that these programs, as I mentioned, are developed by different developers and providers. Some of these tools, couple of them are developed by so let's say Plaxis and Plaxis 2D is now available under Bentley companies. Sigma W is available under GeoStudio, that is a Canadian company. RS is developed by Rock Science, another company developing these tools here. And then there is another company based in Minneapolis, the US, that have developed a couple of these programs under its own entity. So FLAC and FLAC 3D, UDEC and 3DEC, and PFC 2D and PFC 3D, all of them are developed by Itasca International. So that is another company, as I mentioned, based in Minneapolis, that have developed these tools. And all of them are powerful tools with specialty for geomaterials. So they are computer tools that are used just specifically for geomaterials. There are obviously some other general finite element programs that still can be used for geomaterials as well. For instance, ANSYS or APPIH. These are general finite elements programs available, and obviously those can be also used for geomechanics modeling, but because they are general programs, there are limitations for them that you can use for geomaterial. So the programs that are specifically developed for modeling geomaterials have much higher tools and resources for the geomaterial modeling. It's like, for instance, if you want to take photographs, so it's better to use specialized cameras, photography cameras like Canon or Sony, instead of going and use a cell phone for taking photos. So using a specific tool that is designed exclusively for that target that you want to use and analyze. And for that reason, in this seminar, I'm mostly focused on these programs that are developed by Itasca. And then I will provide examples of geomechanics simulation and analysis under these specific programs. I will talk mostly, I will provide more information about FLAC and FLAC 3D, as well as UDEC and 3DEC. PFC, I will talk less about them because this is more used just for granular and particle analysis. And it's more very specific program, but UDEC, FLAC, and FLAC 3D are more used and more common for the geomechanics analysis. So categorizing these Itasca tools, as I mentioned, for continuous modeling, we have FLAC and FLAC 3D. For discontinuous modeling, again, we have UDEC and PFC. UDEC and 3DEC is used for block modeling. PFC and PFC 3D is used for particle modeling. This is a nice and interesting overview comparing the different tools, different Itasca tools. So let's just start from UDEC and 3DEC. As you see, we have these blocks of rock, for instance, that are modeled, and the fractures between the rocks can be also modeled in UDEC and 3DEC. So the difference of UDEC and 3DEC is UDEC is a two-dimensional program. 3DEC is a three-dimensional program. You can develop three-dimensional models with more, obviously, geometrical complexity. PFC 2D and PFC 3D, as we see they are used for granular and particle analysis. And then we have FLAC and FLAC 3D. Again, the difference, FLAC is two-dimensional model, FLAC 3D is a three-dimensional program. And then recently, Itasca has also released another package. It's called FLAC 2D. That is also a two-dimensional program, but has closer coding syntaxes to FLAC 3D rather than FLAC. So in FLAC and FLAC 3D, as I said, we have these grids or zones or elements. However, they are continuous systems, so we have a continuous material here. In FLAC and FLAC 3D, we still have option to develop discontinuities in the model. So for instance, if we have a fault or a fracture, we can simulate that in FLAC and FLAC 3D as well using interface component. However, if we have a system that has abundant numbers of fractures, propagation of fractures and joints, then it's going to be very difficult to develop that kind of system in a program that is originally developed to simulate continuum medium, obviously, correct? So it's better to just get to a tool that is focused on discontinuum modeling. Again, that example of camera, a professional camera for taking professional photos, comparing to the cell phone to taking photo. If you have a system full of fractures or joints, it's better to utilize a tool that is specifically developed for that purpose instead of going to a tool that is mainly used for continuum modeling, but has some availabilities and options for fractures as well, but very limited and for just specific cases. Here is also an example in Itasca programs that I discuss here. There are options to combine the tools that each of these programs are used because obviously they have been developed by same provider. So there are tools that you can couple these different analyses together. So for instance, this is an example of a cross section of a tunnel in a jointed rock, in a fractured rock, that we have surrounding soils, for example, around it. And we can simulate those soil particles with PFC, and then the jointed fractures with UDEC, correct? So we can combine these and develop these hybrid method models for just very specific cases. Okay. So I provided the different categories and introduced these available tools for study. Now, I'm going to provide a quick introduction of FLAC and FLAC 3D and UDEC, and just providing the capabilities of these. FLAC, as I mentioned, we have both two-dimensional and three-dimensional options. There are tools to simulate and analyze thermal and creep analysis. And then for more user-specific calculation, we can also connect them with C++ or Python or Fish programming languages to develop some specific cases. Just an overview of the software for FLAC two-dimensional, and then the FLAC 3D that we can develop the three-dimensional models in it. There are a couple of different features that can be developed in FLAC 3D. As we said, the model is based on zones or elements. We have boundary conditions. We can have structural elements that can be used for any type of simulation. We have internal alterations such as an underground mine or a wellbore drilling inside a geomedium. Then UDEC and 3DEC, as I mentioned, are used for fractured components, and it has different capabilities from geomechanics modelings to earthquake engineering to dams, foundations, etc. UDEC, as I mentioned, is a two-dimensional version. The environment is very similar to FLAC, and then 3DEC, I have it here. 3DEC, again, is a three-dimensional of UDEC that you can simulate systems that have fractures in it. PFC and PFC 3D, again, for particle simulation. And then there is another program, it's called XSite, that is also developed by Itasca, and that is specifically used for hydraulic fracturing simulation. Also, we can use UDEC and 3DEC for hydraulic fracturing as well. I will discuss the differences of these two different tools for hydraulic fracturing simulation, but Excite is specifically developed for hydraulic fracturing case. Okay, so I provided, as I mentioned, the tools and the methods, and now if you recall the procedure for analysis, by choosing the tools, then we get to the constitutive relationship, and the constitutive relationship is a mathematical model that we use to simulate a real case material. So we have a real material in the world, such as rock or soil. And once we want to simulate it in computer simulation, we need to establish a mathematical relationship. And that is called the constitutive model. Depending on the type of material that we model, we have categories of constitutive models: elastic, viscoelastic, and elastoplastic. And we have a wide range of constitutive models that can be used for geomaterial. Again, depending on the type of rock or soil that you are studying, you can utilize different constitutive models. One of the basic and common constitutive models that are used for soil and rock is Moore-Coulomb. And then we have more specific constitutive models as well. One of the interesting things that we mostly deal in geomechanics simulation, specifically for unconventional reservoirs, is the problem of anisotropic in the behavior of the materials. So in FLAG and UDEC, we have options for constitutive models that can simulate the anisotropic systems as well, in both elastic and elastic-plastic condition. And then the next thing that we deal in computer simulation is the properties of the material. So properties of the material are assigned to a computer simulation based on the constitutive model that you choose and based on the values you get from field. So those can be results from testing of the cores that you got from the field, or results of geophysical study and analysis, or the different other methodologies that we use to determine the properties of different stratification of the ground. Okay, so you see that I just do the overview of these methodologies, obviously. The next thing that we deal in numerical modeling is the geometry development. In FLAG and Itasca-based programs, there are different methodologies to develop the geometry. If you are doing the two-dimensional model, you just have a cross-section of the model and you have a two-dimensional geometry to develop. Once you want to develop the three-dimensional models, you have more complexities, obviously, because you get to the three-dimensional model. One of the methodologies is called extrusion, and that's basically simulating a cross-section and extruding that over the third dimension. And then we have availability to develop very complex geometries in FLAG 3D, 3DEC, and PFC 3D. There is another software, it's called Gridle, that is also available by Itasca, and that is used for complex geometry development. And then in the Gridle, we can develop these complex geometries. We can also always use programming languages like Python or Fish to also include complexities, maybe from a database of a GPS points of a surface, for example. You can import that database to the model and develop your geometry of interest. More specifically, with regard to Gridle, I want to mention that the Gridle that is used for complex geometries it's actually a plugin that is connected to Rhino. Rhino is a graphic tool for developing three-dimensional models. So what you actually do is you use the Rhino, that is separate software. You use Rhino to develop your three-dimensional model, and then you use basically a Gridle plugin that connects the Rhino model to your FLAG 3D, for instance, model. And then you can import the complex geometry you developed in Rhino to your Flag 3D, and then you have that geometry in Flag 3D, and then you can go and analyze your model there. We have different options for Rhino, for instance, and the Gridle. For instance, you can have different types of meshing, fine meshes around wellbore, for instance. Yeah, we can also use that for complex fault systems. Let's say this is a fault of an underground reservoir that is developed in Rhino and then can be implemented in Flag 3D, this system. Okay. So, so that being said, what I provided from the beginning of this seminar to this point was an introduction to numerical modeling, a very quick review of the tools, some review of geometry development, and the constitutive model and properties. These are mostly the aspects that you deal in geomechanics simulation. So from here, I'm going to describe some examples of the wellbore stability and other examples in geomechanics simulation. So I start from wellbore stability analysis. So one of the cases that, for instance, we studied as a consultant is wellbore stability analysis of Bakken Formation that's located in North Dakota and other surrounding states. And then it's an unconventional reservoir consisting of different stratifications, mostly an upper shale model, a middle sandstone model, and then the lower shale model. So this study included geophysical data that we extracted from the wellbore. And using those geophysical models, we were able to determine the in situ stresses as well as some of the properties in the model. We also studied the different wellbore stability cases with respect to the direction of wellbore, for instance, the vertical wellbore, horizontal well, and also the directional well. So the modeling procedure consists of the same procedure that we discussed earlier, from idealization of the field condition to geometry development, constitutive model, and analyzing the system. And then we had the opportunity to do both analysis, both two-dimensional analysis of a cross-section of a wellbore, as well as the whole three-dimensional model of that wellbore and the surrounding environment. And the properties we used for upper Bakken, middle, and lower Bakken are summarized here. And as we see, we have the anisotropic properties. For instance, the Young modulus is different for plane of isotropy, and the plane for the direction of the plane perpendicular to the plane of isotropy. Here is just a review of the, that is basically one of our preliminary models in the work that we did to just evaluate the general stresses around there. And then by simulating and modeling it, we were able to study the results. For instance, this figure shows a cross-section of that wellbore and showing the displacement of the wellbore. So as I mentioned, the purpose of this seminar is just showing the tools and available resources, correct? I'm not going to details of these procedures. Just want to show and provide a sense of what availabilities are there for, and what are the tools that are available that we can use. We were able to also run models of the inclined wellbores and then study the model response, for instance, against a well drill. So these are the displacements around a inclined wellbore. We can also study the stresses around the inclined wellbore as well. Another study that we did also evaluating the stresses around the closed-end wellbore. So you see this is a cross section and that shows the end of the wellbore, and we can study that to evaluate the stress state as well as the deformational state as at the end of the well. Okay. Another tool for analysis that we have that's basically includes the flow mechanical analysis. So using of flow for the analysis in our analysis and coupling the mechanical model with the flow. Based on that coupling, we have different types of flow mechanical analysis in these available tools. And then I'm going to provide an example that how we did a couple analysis of flow mechanical wellbore stability analysis in FLAC. So we had material models of the system, and then we have the wellbore. And the scope of this was basically determining wellbore stability under different mud pressure. So by flow mechanical analysis, we are able to apply the mud pressure and flow to the wellbore, and also considering the surrounding pore pressure, we would be able to study the wellbore stability in different mud pressures, and then actually using that for a design of the mud pressure that would be suitable for specific drilling. So as you know, we have two different categories of drilling: underbalanced vs overbalanced drilling, and that depends on the amount of pressure that you apply to the wellbore, amount of mud pressure that you apply, and then depends also on the surrounding stresses, in situ stresses. So in FLAC, we are able to simulate the system and then study the behavior and the response of wellbore based on the level of in situ stresses and the level of mud pressure you are applying. And then by doing that, you can estimate and you can predict the response of the wellbore, if it's going to be from collapse or breakout condition once you have low mud weight, or if you go to the mud loss or loss circulation in case that you have very high mud pressure. And then you can design a system that you get to a stable wellbore. So that's one of the utilities that we use here in FLAC 3D or FLAC to do this wellbore stability analysis. For instance, this is an example for a two-dimensional case, and you see this is the gridding and meshing around the wellbore. At the center that we have the cross-section of wellbore here, you can use much finer elements to have a more accurate stress and displacement contours around that well. And then we can study the results, and then based on the results, we would be able to basically do those analysis and predictions. The results that we are interested in would be in displacement, the stresses, effective stresses, and pore pressure, as well as the state of the yielding of the material around the wellbore. So for instance, this is a study that is done with different mud pressure, and then studying the area that is yielded based on different mud pressure. So mud pressure 15 megapascal, it's relatively low. You see it's a significant area of wellbore is yielded, so we'll have a more displacement here. Once you increase the mud pressure, the amount of yield is going to be minimal. Here is an overbalanced drilling with a very high mud pressure and very limited yielding around the wellbore. By doing that, and you can do design, and for instance, you can determine the NYZA, the normalized yielded zone area, and then you can use that for design of your well bores. This is one of the examples here. Okay, yeah, that was an example showing the procedure for doing this. We can do that also in a three-dimensional model. This is an example of a 3D model of the same situation. And then obviously you can also apply a structural element for casing as well in the 3D model. So you see again that yielded zone in the 3D model. It's ragged because the number of elements are small, are large. The element size are large to just have a shorter computational time. But in a real consulting case, we usually provide much dense elements here. Okay, so the other usage of the analysis would be also the geothermal analysis, that we can do the thermal modeling in FLAC. Depending on the type of analysis, we have the availability to do both conduction and advection models in FLAC, and as well as FLAC 3D. So for instance, this is an example of a temperature analysis around a wellbore. So this is a quarter of the wellbore cross section, and we can see the temperature contours around the wellbore by drilling that wellbore here. And then studying the temperature variations versus the radial distance. Some examples with regard to the distinct element modeling using UDEC. So as we mentioned, the UDEC is used for fault and joint discontinuities. And we can use that for the analysis here. So we use UDEC for hydraulic fracturing applications. As I mentioned, we also have the X-site. So X-site is mostly used for naturally fractured reservoirs, and also we can use that for intact rock and performing hydraulic fracturing there. UDEC is mostly used for systems that are already naturally fractured, and then we want to or any other joints or fractures, and we want to apply hydraulic pressure inside that fracture, and then study the behavior of the fracture once those hydraulic pressure is applied to the fracture. So for instance, one of the applications is, for instance, we can simulate this system in UDEC or 3DEC. We have an area of fracture in the model. We have in situ stresses that we will simulate and apply in the model. And then by the state of in situ stresses, and then by invaded zone, we invade a pressure, hydraulic pressure inside the fracture. Then we can study the amount of fluid infiltration to the fractures, as well as the strain condition, the movement and displacement condition of the fracture as well. So for instance, one of these examples that I'm going to show is using hydraulic fracturing in naturally fractured reservoirs. So for instance, this is an example of a wellbore, or basically a hole that is drilled inside a fractured zone. So you see these lines are all fractured. And then by applying a hydraulic pressure to the internal boundary of the well, we would be able to determine the amount of infiltration of the fluid inside these fractures and inside these joints. This is an example that we actually did. So you see the wellbore is here. After the infiltration and after the hydraulic incitement, we see that the amount of pore pressure is much higher around the fractures around the well. And once you get farther from the well, the pore pressure decreases. You can study the flow rate in the fractures. We can study the fluid velocity in the fractures and the fluid direction, which direction they move. So there are these different options that can be studied. These are, as I mentioned, are modeled in UDEC because it has the potential to and availability in application to simulate an abundant number of fractures in any direction you want. Obviously, these fractures right now are ordered, but you can develop random fractures in the model based on some statistical models as well. And then you can monitor the pore pressure, for instance, at different points and develop pore pressure or any other result changes through time. Other example that I provided is applying hydraulic fracturing in a prescribed crack. That is basically a crack that we apply the hydraulic pressure inside that, and then we can see the response of that crack versus different pressures, pore pressure. So you see the pore pressure is 10 megapascal. The crack is very minimum. You cannot actually see it. Once you increase the pore pressure to 500 megapascal, you see significant detachment and separation in the rock on two sides of the crack. So yeah, so that is basically the end of this seminar. I just tried to provide an overview of tools and methods that are available for geomechanics simulation that is used for reservoir modeling, for wellbore stability analysis, for fracture, hydraulic fracturing and fracture studies, and other applications. This mostly focused on Itasca tools such as FLAC, FLAC3D, UDEC, and 3DEC, and provided the procedures that we mostly use for consulting. So if obviously you have any consulting needs, we are available to help and support and provide consultation on that. The other areas that I actually also work is I also develop courses in this case. In More Academy is an online educational platform for civil, geotechnical, and petroleum disciplines, and I have a couple of courses here. These two courses I developed it myself, FLAC, FLAC3D, and UDEC for geomechanics, and advanced FLAC and FLAC3D for geomechanics. So this is basically the topics that I talk in much more details. Each of these courses include about 20-hour educational material, and for these two specific courses, we provide actually 1 month full license of these programs by Itasca, so you will get access to full license of these programs. You would be able to see the course details here, and then if you watch this seminar, you would be also able to get 30% discount, and you can contact info@moreacademy.com to get that. We have also 2 other petroleum engineering courses at More Academy, including intelligent data analytics for petroleum engineers and Petrel software for seismic data interpretation. These 2 courses are taught by 2 other instructors. So these 2 are taught by me, these 2 by 2 other instructors. Thank you again for enrolling to this webinar. I would appreciate if you have any questions. I would be glad to respond. Okay.
Thank you so much. Thank you so much.
Sure. Thank you.
In your private chat, I placed 6 questions. Some of them are very general, some of them are very special questions. I would appreciate if you cover, and plus that other audience, if they have a question, they can raise their hand and unmute themselves and ask the question. I think Dr. Honarpur has a question. Maybe you can start.
Yeah, sure.
Thank you very much. I'm not a specialist in geomechanics, but on the fluid flow, I certainly enjoyed the presentation by Dr. Zamiran, and particularly in the case of Bakken, which there are a lot of microfractures, and then we do natural fracture. Microfracture as natural, and then we do hydraulic fractures. And then there is a zone upper Bakken, lower Bakken, and it is very complex. I don't know whether any of these modeling are sufficient to handle that situation, because sometimes pressurizing the Three Fork opens some of the fractures in upper buckle. So there is a very complexity. And have you had an opportunity to look at that in a larger scale? Because location of the wells, it's extremely important in Balkan and in other unconventional. And you need a very detailed knowledge of the fractures, existing fractures, and then the model that you use for this complex system.
That's a great question. Thank you for asking. Yeah, as I mentioned, the complexities are abundant, and it's very difficult, as you said, also to simulate all the complexities with all details. As you mentioned also, there are two different approaches. One is just simulating the whole reservoir, and then one is just a concentrated simulation of the wellbore and just surrounding medium for just a smaller scale model. So I assume that if we do the more concentrated scale of a wellbore and the surrounding, it would be easier to simulate those fractures in the systems, for instance, in the 3DEC. But for the larger scale model, for simulating the whole fracture system, as well as the wellbore, and just interaction of these different systems to each other, it adds to the complexity, and also it adds to the computational time, because the model would be much larger. You would need a lot of elements, and it takes much longer for the simulation, and obviously depends on the result that we want to see. What's the output that we want to study for a specific wellbore. So in that case that I provided in this seminar, that is actually simulating the system and simplifying the system into a continuum medium, correct? So in that case that I provided, the effect of those microfractures and natural fractures are not considered, and the thing that is considered is basically evaluating the wellbore response, the deformational and stress response around the wellbore, based on the wellbore dimension, based on the direction of the wellbore, let's say based on the mud pressure, and based on the in situ stresses. And that's the reason we use the FLAC 3D or FLAC as a continuum medium. But if we want to also simulate the fractures, we need to move to the 3DEC. The other thing is there is also a simplified procedure that you can use a continuum medium, but by considering those microfractures, you can reduce the basically a strength of the material, considering those microfractures, but still modeling it as a continuous medium. But if you want to get to the details of, pore pressure, infiltration through the fractures and such kind of thing, then the 3DEC or UDEC should be used. And as you mentioned, there are always complexities for doing that.
Anyway, excellent presentation. I enjoyed it. And I'm proud of University of Missouri because that's where I went and did my PhD there.
Oh, nice, nice.
Many, many years ago. Thank you for keeping the culture.
Sure, thank you. Yeah, I'm actually right now based in Houston. So actually, from the next semester, I will join University of Houston as lecturer.
Excellent, excellent.
Yeah, thank you so much.
Good luck. Bye-bye.
Thank you. So, Dr. Samui, we got also some other questions in the chat room.
Yes. If you want, you can read, or I can read for you. Up to you.
Maybe to have a just interactive.
Yes. Number one.
Can read, yeah.
Which method and program do you advise for salt cavern project?
Mm-hmm. Okay, so I believe that in those salt cavern projects, We also deal with the creep condition, and then we need to consider the creep simulation as well. So using FLAC and FLAC 3D, we can utilize that for such analysis. However, you need to specify a special constitutive model that you can simulate the creep behavior. So there are specific constitutive model for the creep behavior in FLAC and FLAC 3D. And then you need to also purchase, if you want to purchase a license, you need to purchase the creep analysis. That is an additional module to the original software. So by having the creep analysis module and using the creep constitutive model, you can specifically model it in FLAC and FLAC 3D. Obviously, there should be additional programs in the market for doing that as well. Okay, you want to go to the next question?
Sure. There are some general questions I can see. How in your modeling, considering permeability and porosity change?
Okay. So for that, once we simulate the model, depends if you are simulating it as a continuum medium, for instance, in FLAC and FLAC 3D, or discontinuum medium in UDEC and 3D. So talking about FLAC and FLAC 3D for continuum medium, although the model is continuous, but because it's a software developed for geomaterial, you can still simulate the porous medium in the model. So the porosity and permeability are assigned as properties of layers, and then the pore pressure dissipation through the porous medium is simulated in the continuous medium in FLAC. And then you would be able to have either isotropic permeability or anisotropic permeability, having different permeabilities in different directions. And then considering UDEC and 3DEC, you have the option to have the porosity and permeability properties for the blocks, those blocks that are continuous. And also you need to provide the permeability characteristics of a fluid passing through those fractures as well. So those are also input properties. Yeah. So let's go to the next question.
Okay, how accurately in different numerical modeling we can consider different mineralogy and effect of the CO2 and water that they have different physical phases?
Okay. Okay. So with regard to the accuracy, again, as I mentioned, that's the point of idealization that we always have. And obviously, the level of accuracy can be determined by, for instance, verification analysis and simulating the system, and then studying the results, probably comparing them to case studies or to the field measurements, and always trying to calibrate the model. So if you have a proper understanding of field and proper data, enough data field, you can run your model and calibrate and study the results and calibrate your model to have a proper accuracy, your desired accuracy. And then with regard to the CO2, I guess you're talking about the gas modeling, probably, correct, in the porous medium. So
I think that, as mentioned, it looked like considering liquid, gas, and solid at the same time, because they have different phases. How the modeling.
Yeah. So for that one, FLAC and FLAC 3. So in FLAC, we have a two-phase model, two-phase liquid model. But I have studied this area, and I found out that these are not powerful tools for gas modeling. So the FLAC and FLAC 3D mostly are powerful for liquid modeling, but not gas modeling. For that one, I think there is another software that I recall is called Comet 3. You might have heard about that. That is specifically designed and developed for gas modeling in the underground reservoirs. And obviously there are other tools as well, but I don't think FLAC and FLAC 3D would be a perfect solution for that. Yeah. And then you have also another question above that, correct? About the accuracy. That's the same that we discussed.
It's very similar to this one. We can go to question 5. For Bakan study, did you use data for core or well-log outputs?
We are both. So that was a project that we cooperated with University of North Dakota. They had laboratory tests and experiments on cores in University of North Dakota laboratory. And then they have, and then we got the well-log outputs through the field measurements. The logs that I showed, they were from the well-log outputs, but I didn't provide the core examples.
Okay, last one is not question, maybe request. Is it possible to share your presentation?
Sure, yeah. I will provide the PDF.
They can email you, it's better to just...
Yeah. Or you can just provide me the email list and then I can send it to everybody.
Sure, that's perfect.
Yeah.
Perfect.
Okay.
Excellent, excellent. Thank you so much.